Hi everyone, my name is Vladimir Horikov. I'm a software developer at Eastbanc Technologies.
So the presentation is going to be about functional programming in C#, and although all code samples are going to be in C#, the concepts we're going to discuss here are also applicable to Java code bases and any other object-oriented programming language as well. All right, so let's start. We'll start with the question, what is functional programming? You might have heard that functional programming is programming with, well, basically when you program without side effects, side effect-free programming. When you have a data structure, for example, a class, and make it immutable. And that means that you cannot change instances of that class. Or you might have heard that functional programming is programming using higher order functions. Higher order functions in C# is basically C# lambda syntax. Or maybe you do functional programming when you use functional first languages like F#, Haskell, or Scala. Actually, no. While all these three things are related to functional programming, they by themselves don't constitute the definition of functional programming. So what is it then? Functional programming is programming with mathematical functions. All right? Problem solved. That's a little bit of a recursive definition, so let me define mathematical function first. Mathematical function is not a class method in the programming sense. We as programmers usually use these two terms, function and method, as synonyms, but they are not the same thing from functional programming perspective. The best way to think of a mathematical function is of a pipe that gets an input and returns an output. And that's it. It doesn't leave any marks about its existence in the outside world. It only does this one thing, finds corresponding value for any value you feed into it. Mathematical functions possess two attributes. The first one is referential transparency. This fancy phrase basically means that for any input parameter, mathematical function returns the same result, regardless of how many times you call it and regardless of when you do that. So the same input, same result. The second attribute is that signature of mathematical function should have all information about its possible inputs and outputs. And that's basically it. So functional programming is programming with mathematical functions, and mathematical function possesses these two attributes. So let's take an example. Method on the left is a calculate method. It calculates some value given two input values. Method on the right returns the number of ticks elapsed from a given year. So what's the difference between these two methods? The difference here is that, regardless of, despite their functionality, is that the method on the left is referentially transparent. It gives the same result given the same input. So it always returns the same result. The method on the right, on the other hand, doesn't do that. It always returns a different result because this method refers to the global state, which is date time now property. And thus, this method, which is on the right, is not referentially transparent. Let's take another example. This divide method, despite looking similar to calculate method, is not mathematical function either. While so look at this, look at its signature. What can we say about this method just by looking at its signature? We can say that it accepts two integers and returns another integer. But what if we pass 1 and 0 as input parameters to this method? It will throw an exception, divide by 0 exception. So this method pretends that it can process any combination of two integers, but in the reality it has an edge case which is not present in the method signature. So it deceives the caller, the client code, about its functionality. It doesn't convey full information about its possible outcomes to the client code. So this brings us to the notion of method signature honesty. Method signature honesty is another way to state the second attribute of mathematical functions. So the signature of a method is honest when it conveys full information about its possible inputs and the range of possible outcomes. So how can we transform the divide method so that it becomes honest? So make the signature of this method honest. The first method, there are two ways. The first one is we can change the type of the y parameter from integer to a custom non-zero integer type. And that way, we will tell the client, the possible client of this code, that there is some edge case in the y parameter, and that it can turn into any integer except 0. And that way, we will make the signature of this method honest. The second way is to change the type of the output parameter from integer to nullable integer. And this way, we will also tell the caller that the method cannot possibly process any pair of integer values. There are some edge cases for which the method cannot find corresponding value. So these are two ways to make signature of this concrete method honest. So let's recap. Mathematical function possesses two attributes. The first one is method signature honesty, which means that it has a precisely defined range of inputs and outputs. And it also referentially transparent, which means that it doesn't affect or refer to the global state. It always operates the values we pass into it, nothing more. So, so why functional programming? The benefits you get out of applying, yep, sure.
What to this example? So basically, we applied restricting input, providing back global output. But what about declaring that we send out to exception? Like it's also possible.
What about declaring that it can throw exception? Yeah, it's possible. In languages like Java, you can specify that a method.
Well, of course, on one side, it's limitation of the language, but in general, that's.
Yeah, sure. Yeah, actually, it is. It makes, in a sense, it makes code bases written in Java more honest compared to C# because you can specify the exceptions methods can throw in Java, but not in C#. So yeah, that's possible too. Sure. But there are some limitations in terms of what you can do with that exception further, and we will talk about exceptions later in this presentation.
Sure.
Right. So why functional programming? The benefits are benefits boil down to these three points. The first one is composability. When you write your methods as mathematical functions, you're able to treat them in isolation from each other and consider them as building blocks, which you can use to compose a pretty complex functionality without much trouble. So, example in C#, for example, it is LINQ. So, if you used LINQ, you know that it's pretty easy to use all those where select methods, and they allow you to compose a pretty complex functionality. So the second point is that code written in functional way is easier to reason about, and that is a corollary from the notion of method signature honesty, because when you have signatures that fully encode their inputs and outputs, it is possible to know what the method does just by looking at its signature. You don't have to dive into implementation details to understand it. And the third point is that functional code is easier to unit test. The process of unit testing basically boils down to providing an input and verifying the output of the method, the sort. And you don't have to introduce complex test doubles such as mocks in order to do that. And so the process of unit testing is also easier because of that. And all these benefits lead to a greater benefit, which is reducing complexity. And reducing complexity means that you're able to evolve or change your code base with less costs, so your maintainability of your code base increases because of that. All right, these two attributes, method signature honesty and referential transparency, they look quite simple, but they entail pretty interesting consequences. So let's see what those consequences are. The first one is immutability. Before we dive into this topic, let's define our terms. The word immutability itself means inability to change data. So when you define an immutable data structure, for example, a class, it means that once you create an instance of that class, you cannot change it later on. It stays as it is during its whole lifetime. The second term is state. State is data that changes over time. From the functional perspective, state is not just data. It is data that it is the subset of data that changes. So in that sense, immutable classes, immutable data structures don't have states. Don't have state. Only immutable classes do. Finally, side effect is a change that is made to some state. All right. So why immutability is important? Why bother? So remember when we talked about method signature honesty, we discussed that in order for a method to be a mathematical function, it should convey information, it should encode information about its possible outcomes in its signature. When we define a method with a side effect, we hide that information. So the method no longer conveys full range of its possible outcomes in its signature because it hides one of them, one of the components of that outcome in a side effect. So, and that hinders our ability to reason about the code because we cannot possibly tell what the method does without diving into its implementation details. So what we have here is basically this. We have a visible part which is encoded with the method signature and consists of input and output. And we also have a hidden part which is the side effect itself. And the side effect is a problem. The problem which hinders our ability to reason about the code. So what immutability does is it forces you to reveal this hidden part and lift the side effect into the signature level, make it visible, so to speak. All right, so why immutability matters? We discussed the first point, it increases readability of the code. The second point is that you have a single place for validating invariants. So when you create a data structure, class for example, you need to validate the data that comprises that class only once in its constructor. After you do that, you can be sure that the instance of that class resides in a valid state because it cannot be changed after that. And the third point is that immutability gives you automatic thread safety. And what that means is it cuts off a whole set of possible issues related to multi-threaded scenarios, possible race conditions, and so on. All right, so that's why immutability matters. So it's obvious that we cannot use immutable data structures only. And at some point, we do need to deal with side effects. For example, when we save a user, when we change the user's name, we do want it to be actually changed eventually. So we do need to deal with side effects somehow. So how to do that? There are two ways, basically two ways for dealing with them. The first one is command query separation principle. This principle stands for separating your methods into commands and queries. So commands are methods that produce side effects and they don't return anything. Their return type is void. And queries are methods that are side effect free and they return something. So the idea behind this principle is that by separating your methods into commands and queries, you can clearly say if a method incurs side effects just by looking at its signature. So when you see a method that doesnn't return anything, whose return type is void, you can tell that it incurs side effects. It's a command. And when you see a method that does return something, you can tell that it is safe to call it because it doesn't do anything. It doesn't mutate state. So this is the first way. The second, and here's an example. It's a simple customer service class. What it does is not actually important for us. So, but this provides us some example of commands and queries. You can see here the first and the fourth methods are commands. They don't return anything and they do mutate state. For example, the fourth method, save customer method, it saves the customer to the database and it doesn't return anything. It's void. So just by looking at the signature of this method, just by looking at seeing that it doesn't return anything, you can say that it's a command and it's not safe to call it because it incurs side effects. And the second and the third methods here are queries. They don't have any side effects and they do return a value. All right. And although this principle is pretty handy, it's not always possible to adhere to this principle. An example here is stack. The push method in stack is a command. It doesn't return anything, and it does mutate the internal state of the stack because it takes some value and pushes it to the internal collection of values. At the same time, the pop method of the stack is both a query and a command because it returns a value to the caller and it also removes this value from the internal collection. So it mutates the internal state. In this case, it doesn't make a lot of sense to separate the pop method into two methods, a command and a query. So just keep in mind that it's not always possible to adhere to this principle. Right, the second way to deal with side effects is to separate your code into complex domain logic and logic that mutates state. Here's another way to represent this idea. So what we have here is immutable core and mutable shell. So the difference between them is that immutable core is obviously immutable, but it also contains business logic, some complex algorithms or your business rules that comprises the heart of your software. Mutable shell at the same time doesn't contain any complexity, or at least shouldn't contain any complexity, but it does mutate state. So it refers to the global state, mutates data, and so on. So what we have here is a nice separation of concerns where you need to either think about your complex business logic or about mutating state, but never both. So that's basically the principle, command query separation principle, which is taken to the architectural level. And how they operate is the mutable shell provides some input to the immutable core. The immutable core invokes some internal business rules and generates some artifacts. And the mutable shell then uses those artifacts to mutate state. It can, for example, save something to the database, or it can send some email, and so on. All right, that's it for mutability. Let's move on to exceptions. Here's an example. It's a simple ASP.NET action which creates an employee given some name. So you can see it validates name, checks that the name is not empty and it is not null, checks that the length of that name is not more than 100 characters, and that if that validation succeeds, it returns success to the user. And if it fails, it catches the validation exception and returns an error to the user. So the problem with this code is that the validate name method here is dishonest. It hides one of the potential outcomes of this method and doesn't show the user the information about it. So it uses exceptions as a means to generate an outcome, and this outcome is not present in the method signature. And this example is pretty simple, so I'm sure you don't have any troubles understanding it. But let's take some other example. Here you can see the validate name method, which throws exceptions, is put here without a try-catch statement. So is it a bug, or maybe there is some other code upper the call stack which handles those exceptions and processes them? In order to know this, you need to look at every place in your code base that uses that method. You cannot know for sure without that whether it's a bug or not. And that's a common problem with exceptions used to control the program flow. And that's why they are often equated with go-to statements, because just like go-to statements, exceptions allow you to quickly jump from any line of code to the catch statement of the try-catch statement. So pretty much the same way go-to statements allow you to do that. In fact, exceptions are even worse, because go-to statements, they are confined by the method boundary. You cannot jump from one method to another with go-to statement, whereas with exceptions you can cross multiple layers of your application without much trouble. The second problem with exception is that they make code using them dishonest. So not all exceptions, but when you use exceptions to control the program flow. And as I mentioned earlier, that's because you hide one of the potential outcomes of that method behind the scenes. So it's not present in the method signature. And that makes code that employs exceptions to control the program flow dishonest, and that in that sense they are not mathematical functions. So what we have here is basically the same thing as with mutable operations. You have a visible part, which again is encoded with method signature, and you also have a hidden part, which is exceptions. So this time the problem here is exceptions. So how to fix that? To fix this situation, we can adhere to this guideline saying that we need to always prefer return values over exceptions. Unfortunately, in languages like C#, it's not the C# language itself doesn't help us to adhere to this principle, because it's pretty easy to overlook a value returned from a method. And that explains why approach with exceptions might be so popular, because it's impossible to overlook one. It will always show up at runtime. But nevertheless, exceptions that are used in that way for validations, they make your code less readable. So try to always prefer return values over exceptions. So are there any use cases, any valid use cases for exceptions then? There are. So they all can be summarized with this phrase: use exceptions for exceptional situations only. That means that exceptions should signalize a bug in your software, situation you cannot recover from. So some unexpected situation. And try not to use exceptions in situations you expect to happen. In that sense, validations are not exceptional situations, because you do expect the software to be used in improper ways, and you do expect incoming data to be incorrect, at least sometimes. So the best way to think of validation is of filtration, when you filter the incoming data, and only if it passes that validation do you pass it further to the domain model. All right, so any questions about exceptions? Yep.
I was just wondering, what are some cases some problems that do not lend themselves to functional programming? I guess problems that require feedback, where the output of a function becomes the input, and I guess stochastic processes, where you have a random variable, the function has an unpredictable output. I guess so. Those are would those be two or?
Well, if you have output that comes as an input to another method, that's pretty much the definition of function program. So that's
or the same. The same, like a recursive type.
Okay, I see. Yeah. Well, yeah. In this case, you do need to refer to some global state to the random number generator, and yeah, that wouldn't be a purely functional approach in that case. So yeah, that's not exactly functional programming. But as I said, you can try to push all this impurity to the edges of your system, to the impure shell, and use your domain logic, your main business rules in the pure core of your system. So you can try to use the random number generator at the start of your business operation, then pass the result, it generates some random number to the pure function, and then return that result from that pure function to back to the impure core, and then repeat this process again. So you can try to separate pure parts of your application from impure parts, and that impure parts, they will contain referrals to the random number generator. So you can try to do that. Right. Yep.
So more to the exception situation. Let's take an example that I'm trying to read a file, and I'm succeeding or not succeeding depending on whether the file is there or not. By iteration system API, if file is not there, I'm getting back an exception, right?
Mm-hmm.
So to overcome that, I can first check whether the file is there or not, because it's expected situation that file not
there. Yeah, I see the question.
There.
Mm-hmm.
So I can check up front whether the file is there and only then try to read it. But between those two calls, the file still disappears. I still get an exception.
Yep. So the guideline that I didn't mention here is that you need to catch known exceptions at the lowest level possible. So this exception that you're explaining here is a known exception. So you're expecting that the file system will throw at some point file not found exception, for example. And if you do expect some other component, some third-party library to throw, you need to catch that exception and convert it to a return value. So you're placing the try-catch block at the lowest level possible. At the catch statement, you look exactly at the type of the exception you're expecting to happen, and then convert it to return value. So this way you're still adhering to the functional principles, at least at your part of your code base. Some other parts, third-party libraries, they still can throw, but you convert them, those exceptions, to return values, and then go from there with those return values.
Okay, so now I unwrap all.
Okay.
Let's say that I'm expecting not enough memory exception, right? And all over the code we have this return new object when we instantiate a new object.
Okay.
For me, let's say for our application, to have out of memory exception is expected behavior.
It cannot be expected because when you have an out of memory exception, it's
well. Let's say that we change our behavior when we get to that state, but we cannot put this check in every place, right? That need to be some generic.
Well, in this situation, out of memory exception actually cannot be expected because you expect to have some memory to execute the program. I'm not sure it's entirely correct example, but I see what you're saying. In this case, actually, for all those exceptions, ambient exception, for example, thread abort exception, out of memory exceptions, what you need to do is to place one generic try-catch statement at the top level of your code base, and in this case, you just show a generic error to the user, say that something went wrong and you need to shut down everything because something unexpected happened, and log this exception somewhere and then just close.
Logging is also side effect, right?
Yes, but that we can treat it as impure shell, which is not part of our pure core. Yeah. So as a general rule, these exceptions that can happen anywhere, they cannot be expected, and thus they do fit the definition of exceptions, which are used to define some unexpected situation. Right? That's kind of yep.
I have a question. So how do you normally handle this exception? Do you just waiting for the error pop-up messages and then you fix it, or you will have some process you think will happen?
So I think, in my opinion, the best way to handle those exceptions is to let them fail your application. So the fail fast principle. So when you do see an exception which is unexpected, which you cannot handle, the best way to process them is to just let them propagate and fail your application entirely, or if it's some stateless application, for example, ASP.NET application, then you just fail the request that generates this exception and tell the user that something bad happened, cannot possibly go further, and so on. So after that, you can analyze your errors. So this situation should be logged somewhere. After that, you analyze this error and do something with that. So that way, you're just processing unexpected situations and convert them into expected. So you can then add some code to your code base that will process that exception, and that will convert it essentially from an expected one to an expected one. So fail fast principle is another important guideline here, because when you use generic try-catch statements, when you just look for a generic exception and then and do it in your code everywhere, it's not the best way to handle them, because that way you're hiding the output. Well, you're hiding the failure essentially, because when you have an expected exception, that's a failure because you didn't expect some exception and it happens. You shouldn't hide it. You should reveal it on as early stages as possible. Right, let's move on to primitive obsession. Primitive obsession stands for using primitive types for domain modeling. Let's take an example. Here's a simple user class with a single email property, which is represented as string. What can you do to ensure that no user can create it with an incorrect email? Well, to do that, you can put guard clauses. By the way, that is correct use of exceptions, because these exceptions are not used to control the program flow. They are, when this exception happens, it means that something wrong in your code base. You didn't verify the email beforehand and let it pass through. So this is an invariant violation, which means a bug in your software. So when you want to, yep.
I just want to check, is it some sort of assert statement?
Yeah. So when you want to check that no user can create it with an incorrect email, you just put guard clauses, assertions, essentially here, and that's it. And if you have another class organization which also has an email, and you want to also make sure that no organization can be created with an incorrect email, what you do, you also put the same set of guard clauses to the organization's constructor. So what we have here is duplication of the domain knowledge, of the knowledge regarding what constitutes a valid email. All right, that's the first problem. The second problem with primitive obsession, so primitive obsession is that we use the primitive type string to represent a domain model, the domain concept, which is email. The second problem with primitive obsession is that they make your code dishonest. So here's an example of a method that creates a user given some email. So what you can tell by looking at the method signature, you can say that it accepts a string and it returns a user. But what happens if you pass, for example, an empty email to that method? It will throw an exception, because an empty string is not a valid email. So what we have here is a dishonest method signature, because it deceives the caller, pretending that it can process any string, any incoming string, whereas in the reality it can process only a subset of those strings, which constitute a set of valid emails. That's basically the same problem as with the divide method, which we saw previously. So both these concepts, email, both these parameters, email and y, the concept behind them are less, well, they are more fine-grained than the types we use to represent them. And what I mean by that is subset of valid strings, subset of valid emails is a set of valid emails is only a subset of valid strings. So we shouldn't use a set of strings to represent an email. We should specify that this method accepts an email, not string. And by the way, if you have any questions, feel free to interrupt me. All right, so the same thing as we had with the divide method. So two problems with primitive abstraction. It makes our code dishonest, and it violates the try principle, the don't repeat yourself principle, because it encourages domain knowledge duplication. So what to do with that? We need to wrap primitive types with separate classes. And we don't want to do that with all primitives, of course, only with those that have some invariance attached to them. For example, an email has some domain knowledge, some invariance attached to it regarding what constitutes a valid email. And here's what we get when we apply these principles in practice. So here, instead of specifying that method accepts a string, we explicitly saying that this method accepts an email, not string. And that makes this method honest, because the potential reader of this method knows that this method doesn't accept any string, only a string that represents a valid email. And that's basically the same thing we did with the divide method when we made it honest. We replaced the integer with non-zero integer type. Right. So getting rid of primitive abstraction leads to these benefits. It allows us to remove duplications. It makes signatures of the methods honest, and it also allows us to employ a stronger type system. So what I mean by that is, when you have, for example, if you have a username and an email, you can accidentally mistake one for another and pass an email in places where username is required. And the compiler wouldn't say anything about that. That would be a perfectly valid program. But if you extract username in its own class, or an email also in its own class, it will not be possible to do that, because compiler would notify us about that. So it will not be possible to pass an email in place where username is required. Yep. Any questions about primitive abstraction? All right, let's move on to nulls. So here is simple code sample. Yep.
Sorry, I have a question.
Yep.
So should that principle be applied to like non-primitive types as well, to make sure that validation is thorough on those as well? Because it could happen where we have a subset of non-primitive types.
Yeah, absolutely.
Derived from another non-primitive type.
Absolutely, yeah. So if you have, for example, a range from one thing to another, it's also preferable to combine it into a separate class and explicitly define the invariance of that separate type. So in the case of range, it's also primitive, of course, but it has two primitives, for example, date from and date to, and an invariant that that you can explicitly define here is that the date from cannot be more than date to, and that makes the code that works with that range much simpler because it doesn't have to validate the same invariant all over the code base. So yeah, absolutely, it doesn't necessarily apply to primitive types only.
So basically the way you try to handle it is when you pass in a parameter or maybe object, you make sure that's a right object, maybe a right type to avoid the issue.
You mean this sample code?
Yeah, something like that. When you pass in an email, you make sure the email is a
Yeah, so
kind of email object.
yeah, that's right. So we do need to ensure that we do need to validate the email somehow before that, and to do that, you actually can. I'll show you it. Well, I can show it right now actually. So here's sample code, which I was going to show later, but I will show it right now. And so to validate the email, so you do need to validate the string and convert it to an email before passing it further. So the way you can do that is this one. So you create a factory method, email create, which returns a result of email, and this method tells you explicitly that the conversion can fail at some point, and this result tells you that not all possible input values convert to an email. And then when you have this, you need to explicitly verify in your code base that this conversion was succeeded, and if it's not, you need to return error to the client. All right. So, yep. Moving on to nulls. So this is simple code sample, and I'm sure you encountered it a lot in different code bases. In fact, we as developers are so accustomed to the use of nulls that we rarely notice any drawbacks in this approach. But there are some drawbacks, and so substantial that the inventor of null, Tony Hoare, called it his billion-dollar mistake. It has caused $1 billion of pain and damage in the last 40 years. And some might argue that it's more of a $1 trillion mistake at this point, by now. So what's the problem with nulls? Here's an example. Can you tell just by looking at the method signature if it can return null? If this employee type is a class reference type, then you cannot, because it can turn into null. And in order to see if this returning value can turn into null at some point, you need to look at the implementation details and see if there is indeed some branches that return a null value in this method. Here's another example. This is a simple repository that returns an organization given some ID. So what happens if you pass an ID which is not present in the database? Will it simply return a null, or will it throw an exception? You also cannot possibly know that without looking inside, because the signature of this method doesn't tell you anything about that. So the problem, this is the problem with methods. This is a common problem with methods that employ reference types in their signatures. Because when we define a class in C# and actually in Java and many other code bases as well, when we define a class, what we actually do is we define a two-fold class instead, which either can contain a null or it can contain an actual instance of that class. So when we define a function which accepts an integer and returns an instance of that my class, what you actually do is you define a function that returns an instance of that my class or null, that two-fold class instead. So sometimes that's exactly what you need, but sometimes you just want to define an output as a my class without the possibility for it to turn into null. And the problem here is that in C# and Java and other code bases, it's not possible to differentiate between them. It's not possible to distinguish between nullable and non-nullable reference types. So how to mitigate this issue? To mitigate this problem, we need to introduce a maybe type, or you might have heard about it as option. In F#, in Haskell it is called maybe, and I'm sure it has some other synonyms as well. So what you need to do is you need to agree upon the convention within your team that whenever you need to introduce a variable which can potentially turn into null, you will use the maybe type instead of the underlying plain type. And this way, you will be able to make signatures of your methods honest. So here, for example, if we're creating a method that can return null at some point, we can explicitly define that possibility in its signature. So instead of organization, we're saying that the return value is maybe of organization. And that means that the method can return an empty value at some point. And here is, and that way we will be able to distinguish between two types of methods. So the method on the top does potentially return value null, and the method on the bottom doesn't do anything. So it returns non-empty values. All right. So this way we made this the signature of this method honest, the same way we did with the divide method when we changed the type of the output parameter, the output value from integer to nullable integer.
So you're just covering your exceptions to the functions, where the function is undefined. You're just plugging it in and saying this is what happens when you plug in something that's undefined. Return this.
Yeah, so you basically make it explicit. So you make explicit the possibility for something to turn into null, so that you don't have to check for that null later on. You don't have to wonder if this variable or if this parameter can turn into null. You don't have to put everywhere the checks nulls, essentially.
So for the second function, we put a question mark the integer.
Yeah, that's because it's a struct, and in C#, the nullable structs they have this syntax. It's basically the same as nullable of integer. Yep.
So, a billion-dollar question. So before that, when we just introduced, yeah, just do the last one. So
Some more?
before that, when we say that, well, we should not throw exception, we should return some value back.
Yep.
We switch to another approach. Now that we see a function, we don't know whether it's the old approach or the new approach, right? We don't know whether it's a throw exception or return null. Now that we went one step further and introduce this maybe, when we see maybe, we know that it might return null.
Yep.
But if we don't see maybe, we still don't know whether it will return exception.
That's a good question, yeah. So the way to mitigate this problem is to use aspect-oriented programming. So there is a library, null guard, fuddy null guard library that allows you to interweave your assemblies in a way that it will insert assertions in your code in the input parts and in the output parts. So whenever you return something, it will insert the assertion that this return value is not null. And that would allow you to basically convert those nulls into exceptions, back to exceptions. And those exceptions would mean that you did something wrong and you need to fix that.
The whole circle back.
Yeah, but those exceptions are not used to control the program flow. They are basically unexpected situations. So when you, and to fix that, for example, if you have method that returns my class and you forgot to replace it with maybe my class and you return null, this library, what it will do, it will throw an exception instead of returning null. And this way you will know that you need to change the type of the return value to maybe of my class. All right, let's move on. Oh, it's demo time. So what I want to show you is a simple, not simple, but short example of a code base in a state before refactoring and in the state after that. So here is a customer controller, and what it does is this method, for example, creates a customer given some model, and here you can see that it validates name, email, and to do that it uses exceptions. So for example, validate name method throws business exception, and validate name method does the same. Those exceptions are then caught in this catch statement, and and 404 response is returned to the caller. So the problem with this code is basically that it uses exceptions to control the program flow. It uses exceptions to validate the input parameters. Here is class customer, which is, well, as you can see, it consists of name, primary, secondary email, nothing special. But as you can also see, these name and primary email are represented as strings. So what we can do with this code base is we can transform it so that, for example, the customer method will now explicitly specify in its constructor that it accepts only certain types of strings. So here, instead of string customer name, we defined a special type customer name, special type email, and as the secondary email is not required, for example here, it is not required, but you cannot possibly say if it's required or not, because there is nothing in the signature that tells you that. But here we explicitly specify that it's a maybe of email, and that way we specify that this secondary email is not required for us to work. And to convert exceptions, to remove exceptions that are used for validation, you can do this. So you can transform the incoming data into domain classes, customer name, email, maybe of email, and then use special helper class to combine possible errors. So what this result combine does is it combines these four results into a single one, and if there are anything wrong with those results, it generates a faulted result, which you can then verify. Well, look inside, and if it's failed, you can return an error to the user. So here you can see no try-catch statements, and all primitives are converted into domain classes, and that's basically an example of applying functional principles. Another just simple example. I didn't mention that, but it's also pretty much, well, it's also handy to use this approach. So for example, here you can see we get a customer by ID, verify its name, verify some business rules that it can be promoted, then we promote the customer, then we send some promotion notification, and so on and so forth. So what this code can be converted into is this one, when we basically combine all those operations into a single chain, which looks much better, at least to me. So, and it's also shorter. So here you can see we get the customer by ID, and it returns a maybe. We convert that maybe to result. Then we ensure that customer can be promoted, and send notifications, and so on. So that's basically it for our presentation.
let's probably recap what we did here. Yep.
If call, let's say, to result on the maybe object, and if it's null, what will be returned?
Let me show you. Yeah, sure. So if you call to result, and if it's null, it will generate a faulted result with this error message. And if it's not empty, then it will generate.
Is it because maybe implements to result?
This to result is just a helper method that allows you to convert maybe to result. So why we could potentially use maybe in places where result is required, but that would be that is not the best approach to that, because maybe and result are different kind of types, different kind of monads. Well, I shouldn't say monads, different kind of types. So maybe basically tells you that if something returns you nothing, if something returns you, if you see that some method returns a maybe, then it can potentially turn into null. But if you see that some method returns a result, then you can say that some error happens. So while maybe can return null and it is expected situation, with result you have failure, and that means that something wrong happens. And if you probably generate, well, if you try to do the same twice, the second time, then you will probably do different, get different result. So to your question, how this works is, let me see. So to result, it just gets this maybe, checks that it has some value, and if it's not, returns a failure. And if it does contain some value, it returns a succeeded result. And I'm using C# function extensions library for that. And that's a NuGet package that I created for these types to combine them into a single place.
Can I see the function where you created the object?
Sure. Here it
So I
is.
see that you're handling the secondary email differently than the primary email. So you have a different way of doing it for a maybe type.
Yes.
You're not creating it directly. So can we see what's happening in the get secondary email?
Yeah, here it is. So the difference between them is that the secondary email can turn into null. So this null thing is an expected situation, and so we need to return an OK result when it happens. So this struct here, when you have a result of maybe of email, means that some operation can fail, but it can succeed. And when it succeeds, it may either return something or return nothing. That would also be a valid return result. The difference between that one and this one is that here, if some operation succeeds, it always returns non-empty integer. And yeah, that's why we use a separate method to do that. So we check that secondary email is null, and if it is, we return OK because it's a valid situation. And if it's not null, then we try to convert that secondary email to an email, and then convert the result to a maybe of email. That function map, it converts a result of one type to a result of another type. So it helps you to convert the result of maybe to a result of convert a result of email to a result of maybe of email.
So what kind of business logic would you have in the combine function? Where could you be checking that?
Yeah, sure. It just combines all the possible error messages that you have in results, and you just aggregate them into a single result, and that's it. Yep.
You use the term business logic, and that just sends me to thinking in a certain direction. It seems like so many problems in, say, economics or business require you to change the function based on the input, change the function based on the rate. Say, for example, calculating your taxes. They use multiple different tables, and I call those tables all different functions depending on your income. And if you're over 120K, then you're using an entirely different system to calculate your taxes. So that doesn't lend itself to functional programming, does it? If you were to say, write something like TurboTax or say something like this, or say calculating your insurance based on the number of accidents that you've had. So that you might use a different, so say if this guy has a couple of accidents within a certain time window, then you use this to calculate his premium.
Mm-hmm.
And if he has 4, then you use this to calculate it, and you incorporate all of these other different factors to calculate his premium. So like what problems, I'm imagining there are a set of problems that lend themselves to functional programming, and then another set of problems that do not. So what are those problems that do, and what are they called? Do they have classes?
Well, actually, what you explained, I think it also this problem also fits the functional programming principles as well.
Okay.
Because what you have is just different kind of logic that you can invoke depending on the incoming input parameters. So when you are saying that a user might have a certain number of incidents, and depending on that number, you either invoke one operation or another. It's also just a function. You can.
Right. So that's what I was thinking. So what's the definition of changing the state of the function? Immutable programming means it doesn't change the state. The function doesn't change the state. So,
but you can create
that was changing.
But state. You can create a new instance that would contain new data. So you don't mutate the existing instance of something, or some data structure, but you create another one, and this another one will contain the new version of the data you need. So basically, instead of changing the existing instance, you just create a new one, and that.
Okay, so that's immutable data.
Yeah.
But what about changing the state of the function? That's like the definition of functional programming, right?
But
the function does not change its state.
Yeah, but you don't need to change the state of the function. You just can define 2 functions and invoke either of them depending on some input parameter.
All right. So what does it mean to change the state of the function? What does that mean? If you can have an umbrella that covers all these different functions, then what does it mean to change the state of a function?
Well, usually you don't change the state of the function. You usually change the state of some data store or some data structure. For example, when you say something to the database, this is a change which has happened to the state of the database. Right. And when you mutate some field in the class, that's also a change in its state. I'm not sure.
So everything qualifies as functional programming.
Well,
because there's nothing that okay.
Well, not everything. If you remember, definition of mathematical function is when you don't have any. You have methods that are referentially transparent, so that they don't refer to the global state. For example, in your situation, referring to the global state would be, saving something to the database or getting data from the database. But so when you already have that data retrieved from the database, you can transfer to the realm of functional programming and pass that data to the functions, to the methods that are written as mathematical functions, and then they generate some result, some new immutable instances of some classes, and then you can use those instances, that result, to actually mutate some state inside a database, for example. So you have, as I said, you have a mutable shell which generates, which provides some inputs, which is retrieved from the database, for example. Then you enter the area of functional programming when you have your mathematical functions. And when it's done, you get those outcomes that those methods produced and save them somewhere. So apply it to some state. So actually, yep.
So what about that definition, the example that you gave? One was a functional programming and one was not functional programming. And the one that was not functional programming had a date function in it, which was...
yes, that's an example of referring to the global state. Yeah,
yes,
so here it is. Yeah, so this property is not passed inside the function as an input parameter. So it refers to this global property from the inside. So if we convert it to an input value, for example, like that,
then it's functional programming.
Yes, then it's functional.
Okay.
Yeah, if you do it like that.
Thanks.
Yeah, sure. So just want to recap. Oops. Just wanted to recap what we discussed here. So functional programming is programming with mathematical functions, and mathematical functions are methods that possess two attributes. They are honest, their signatures are honest, and they are referentially transparent. Side effects and exceptions make your code dishonest about the outcome it may produce, and primitive accession makes your code dishonest about its input parts. Nulls make your code dishonest about both its inputs and output, because they can be present both in the input parameters and in the output parameters. And I have a separate course on this whole topic, which dives into the detail of this topic and much deeper, applying functional principles in C#. And if you want a trial, actually have some trial codes that will give you 30 days access, unlimited access to Pluralsight. I don't have them in physical form, but I do have trial codes, just digital numbers. So if you want to have them, just let me know, and I'm available at that's my email, Twitter account, so on. So just let me know, and I will send one to you. Right, that's it. Thank you everyone for coming, and I hope you enjoyed this presentation.